Hello, and welcome to Research Methods Part 2, How Psychologists Ask and Answer Questions. I mentioned it in the Research Methods Part 1, correlation studies. We're going to start talking about that now. Correlation studies just show a relationship between two or more variables. An example of this could be parental involvement in academic achievement. So they can both be the cause of the other. So let's say you have an A+ student. So do you have an A+ student because your parents are more involved with you, because they're so proud of you, and so because they spend time with you, you get that A+? Or is it because you're smart and you get that A+, so then that's why they're proud of you, and then they spend more time with you? You know, a correlation just shows that there's a relationship there. All right, it doesn't prove anything, and that's key. All right, it doesn't prove anything, it just shows there's a relationship. All right, so you're an A+ student, your parents spend time with you. Both reasons, could be the reason why your parents spend more time with you, but it doesn't prove one way or the other. One of the key things to remember is correlation is not causation. If you remember from the last set of notes, the only thing that can show causation is an experiment. All right, so with correlation studies, all we are doing is showing that there is a relationship there. Now, you can't determine cause and effect, you only describe the relationship, and that is key. So remember, it only describes a relationship. Doesn't prove anything, it's just describing what it sees. All right, so now I'm going to show you some examples of what correlation might look like when you have data with an experiment, with a study, not an experiment. How do you show correlation? You use a scatter plot. That is key. Make sure you know what a scatter plot is. All right, so you use the scatter plot to show patterns of correlation. The correlation coefficient is used to measure the relationship. Now I'll give you some examples. The plus or minus or positive negative shows which direction the correlation is going. The number indicates the strength of the relationship. I'll show you some examples on the next slide, but it goes up to 1. 1 is the strongest, shows the strongest relationship. If it goes up to the right, like number 5, that shows a positive relationship. If it goes up to the left, like number 1, that shows a negative relationship. So look at number 2. Do you think that has a positive or negative relationship? If you said positive, you are correct. So what about number 6? If you said negative, you are correct. Now 3 and 4, so what you do, you draw a best fit line, but you can't really draw a best fit line with 3 and 4. So that shows that they have no relationship. All right, and the closer to 1 you are shows a stronger relationship. So these 1 and 5, 1 would be a positive +1 because they're just in a straight line. That is number 5. Number 1 would be a negative 1.0 because it's all in a completely straight line. Number 2 and number 6 would be, so number 2 would be about 0.84 because it shows there's a strong relationship there, but it's not 1. It's not all in a straight line. Number 6 would probably be about negative 0.8. And if you see, you'll see some of this in your textbook. Like I just said, the top one, this is a positive 1, as you see here. Right? There's a positive correlation here. The middle one, the data points are all over, so there's no relationship going on. And then the bottom one, it goes up to the left, right, in a completely straight line. So the correlation coefficient is a negative 1.0. So here's another example. All right, so this is kind of like I think it was number 2 on a couple slides ago. It goes up to the right, as you see, so we know it's a positive correlation. We see the number here is 0.84. This is the correlation coefficient. This number I just circled. A lot of times you'll see it on a graph with this, the R equals and a number. So we know it's positive because it goes up to the right. It's a pretty strong relationship. The data points are pretty close to each other. There's a pretty good best fit line going on there. It's close to 1. It's not 1.0 because that's the strongest you can get. Now this one, you draw a best fit line. It kind of goes up to the left a little bit. So we know it's negative. The correlation coefficient would be negative 0.35. Once again, you see it here with the R on the scatter plot. All right, so it goes up to the left or down to the right, however you want to say it. This is a very weak relationship. All right, so 0.3, that's not close to negative 1. All right, the closer to negative 1, the stronger the relationship would be. Right? So because this is a weak relationship, your data shows, it doesn't show that there's any kind of real correlation. These numbers could have just happened by chance. All right? So you wouldn't use this study to, well, it wouldn't prove anything, but to show a relationship at all. So these dots are all over the scatter plot. Right? You can't determine that there's any type of real, true relationship with that. You need a strong relationship, either close to negative 1 or close to positive 1, to prove or to show a relationship. Here are some examples. A lot of times we see things and you hear it in the news, especially if you follow politics, about, oh, this is happening because of this. Well, here are some examples of correlation and not causation. All right, so if you look at this one here, it talks about, if you look at the plot, the blue is ice cream sales and the red is shark attacks. Well, if you notice, as ice cream sales increase throughout the year, so do shark attacks. So does ice cream sales cause shark attacks to happen? Of course not. All right, so correlation is not causation. There's a couple here that are small, that's hard to see. One is the divorce rate in Maine, the top one here, divorce rate in Maine, versus consumption of margarine. So if you eat more or less margarine, is going to cause you to get divorced. Of course not, there's just a correlation there. The next one is Nicolas Cage movies. If you know him, he's an actor, and female editors of the Harvard Law Review. All right, so whenever Nicolas Cage has a movie, there tends to be a female leader in the Harvard Law. The last one is number of people who died by becoming tangled in their bed sheets. Apparently that is a thing. Versus the total revenue generated by skiing facilities. So somehow skiing and dying in your bed sheets is related. Of course not. There's just correlation there. If you look hard enough, you can find correlation in almost anything. All right. So here is the umbrella. Notice every time someone has an umbrella out, it's raining. So do the umbrellas make the rain happen? Of course not. All right, you bring it out because there's rain. The last example is Facebook driving the Greek debt? If you notice, Facebook users back in 2005, it was developed in 2004. Facebook was. If you notice the users, so a year later you already have 5.5 million users. It keeps growing as the years go on, and so does the Greek debt. So somehow Facebook caused the Greek debt. Of course not, right? There's just correlation there. Another great one I found online, and if you search online, you can find these all over. Right? So the headline says, women who own horses live longer. So there's an implied correlation there, right? Horses make you live longer. But in reality, if you own a horse, right, you probably have some money, therefore you can afford health insurance. And that is why you're living longer. Another example of correlation. So some correlations just don't exist. And there's a vocab term called illusory correlation. This is seeing the relationship one expects in a set of data even when no such relationship exists. So stereotypes are a great example of illusory correlation. So one example of this could be, a man believes all people from small towns are nice. Therefore, anyone he meets who is nice, he assumes is from a small town. All right, so, oh, you're nice. Oh, you must be from a small town. You assume, right? You stereotype nice people as being from small towns. And then the exact opposite, right? Because if you're from the city, if you're from an urban area, you must be mean or rude because of living around all those people, right? So if they see someone be rude, oh, you must be from the city, right? Of course, this isn't true. This is all based off stereotypes, right? Plenty of nice people that live in the city, plenty of mean people, right, that live in the country, that live in rural areas. All right, so now the end of our research is going to be talking about data. Hopefully a lot of this is review, like mode, mean, and median. So this is what you've learned in math class, hopefully a long time ago. And I'll show you some examples down here. Mode is just what happens the most frequent, right? So you have all these data points, and the mode is whatever number you see the most. That is going to be your mode. Your mean is your average. All right, so we all learned how to get the average. You add all the numbers up, divided by how many data points you have. And median is whatever you find in the middle. So if you lay all the numbers flat, like on a timeline, whatever number happens to be in the middle would be your median. So if you look below here, here are some examples. This is income per family in the thousands. Right, so you have all these, so each green person would be one family. So if you look at the mode, which number do we see most here? It would be 20, right? So you have what, 1, 2, 3, 4, 5, 6, 7 families that make $20,000. Right, that's the most of any of the things here. The mean is 70,000, even though you only got 3 people that make more than 70,000, right? That's 710,000, right? Puts the mean a lot higher than it probably should be. That's why a lot of times a lot of people like median better when you're talking about data. All right, so if you add all these numbers up to 710, 475, 90, 50, all those numbers, and then divide it by however many data points you have, you come up with the average or the mean. In this scenario, it is 70. And the last thing is the median. If you take all the data points and put them on a straight line, whatever number happens to be in the middle is your median. So if you do that for all these data points here, right, the 215s, the 820s, the 425s, right, the 30s, the 35s, you will find that 30 would be smack in the middle. Measures of variation. All right, so you notice the bolded words once again are vocab words you should know, or you should spend extra attention with. Range is the gap between the lowest and the highest number. So if you take all your data points and you once again you put them on timeline, the range is between, you take your lowest number and your highest number, that's the range. That's the gap in between those two. Standard deviation is a computed measure of how much scores vary around the mean of the score. If we are in class and we have time, I usually do a cookie lab where you guys have to count the chocolate chips, and then you do the mean, median, mode, and you do standard deviation, and I'll give you the formula of how you figure it out. But what you really need to know for standard deviation is what happens. All right, so once you compute it, you get your average, which is in the middle here. This is a bell curve, a normal distribution. All right, what you need to know is that all the data points, or 68% of the data points I should say, all right, 68% fall within one standard deviation. So you can notice that here, right? About 34% above, 34% below. Within 2 standard deviations, that would be this line here, you're going to have 95% of all the data would fall within there. And within 3, you have like 99.7%. I'll show you an example of this later in the year when we talk about IQ scores, right? So the average IQ is 100. Well, the range for average IQ is between 85 and 115. That would be one standard deviation, right? So standard deviation for IQ is 15 IQ points. So everyone within 85 to 115 has an average IQ, right? That would make up roughly 68% of people. Well, if you add another 15 onto that, so now we're up to 130 and down to 70, right? That's within 2 standard deviations for IQ. So that would be 95% of the population, right? So if you're from 70 to 85, you have a below average IQ. If you have 115 to 130, you have an above average IQ, right? So the 95% of people fall within there. And then if you go above that, right, that's where you fit in everyone else. Another 15, that's when you start getting to the gifted and the intellectual disabilities. All right, last slide. And once again, hopefully if we can be in class, or maybe I can have you guys do this at home, the cookie lab. There's 2 different types of statistics we'll be talking about. We're talking about descriptive statistics and inferential statistics. A descriptive statistic, that just summarizes the data numerically, right? So that's the mean, the standard deviation, or graphically, right? So you have to graph, whether a bar graph, the histogram, something like that. Inferential statistics uses patterns in the data to draw inferences about the population represented, accounting for randomness, right? So you look at the data and then you use patterns in that data to make inferences about what you're talking about. And this concludes Research Methods Part 2.